There are some laws in physics that are just everywhere. What if I told you that the same exact rule that can save a raw egg in a car crash is also at play with spacecraft getting hit by tiny particles at insane speeds? And what if that same rule could help us solve a 100-year-old argument at the very heart of quantum physics? Well, today, that's what we're doing. We're digging into one single universal law that connects it all.
All right, so here's our game plan. We're going to start with a super simple classroom experiment, then shrink way, way down to the micro scale to uncover a brand new universal law. And finally, we'll see how all of this ties into the wonderfully weird world of quantum mechanics.
So let's kick things off with something you might have even done yourself back in high school physics class. It seems simple on the surface, but trust me, there's a really profound secret about how the universe works, hiding inside.
Here it is, the big puzzle. It's called the paper car crash experiment. The goal is to build a car out of just paper that can protect a raw egg. Sounds impossible, right? But it actually works. The secret isn't about making the car stronger, though. It's all about making the crash last longer.
And this all boils down to a key concept in physics called impulse. Okay, imagine a truck. To stop it, you've got two options. Option one, it hits a brick wall. That's a massive force over a split second. Not pretty. Option two, it plows into a giant haystack. Now that's a much smaller force, but it's spread out over a much longer time. The cool thing is, the change in the truck's momentum is exactly the same in both cases. By extending the time of the crash, you slash the force. And that's exactly how those paper crumple zones save the egg. Okay, so we've got the basic rule down. Stretch out the impact time and you reduce the force. Simple enough. But does that rule hold up when we move from a paper car to something way more extreme? Let's take that idea and push it to a whole new frontier.
Yeah, suddenly that paper car challenge seems kind of quaint, doesn't it? We're now talking about hypervelocity impacts, like tiny micrometeoroids smacking into a satellite or a bullet hitting body armor. At these speeds, with things happening in nanoseconds, the old physics rules just start to fall apart. Scientists really needed a totally new way to look at the problem.
And this is where the science gets incredibly cool and incredibly small. You're looking at what these hypervelocity impacts actually do on a microscopic level. The key thing to know is that at this scale, with crashes over in the blink of an eye, our old models for predicting damage just didn't work. It turns out researchers realized they were focusing on the wrong thing entirely. See, for a long time, the models were all about energy, how it gets distributed and absorbed in a crash. But honestly, it was a mess. You needed a bunch of custom fixes for every single material, and even then, the models would fail at really high speeds. But then, researchers tried something different. Instead of energy, they decided to focus on momentum transfer, the impulse itself. And that changed everything. This new way of thinking wasn't just some neat trick to make the equations prettier. Oh no. It uncovered something absolutely astonishing, something that took all the chaotic, messy data from all these different impacts and brought it all together under one simple, elegant idea. So, scientists at the University of Wisconsin-Madison just went all out. They did a ton of experiments. They were firing these tiny projectiles at all kinds of stuff, polymers, composites, you name it. They tried different sizes, different shapes, different speeds. They were hunting for a pattern in the chaos. And boy, did they find one. Okay, I know this graph looks like a crazy mess of data, right? But stick with me, because the story it's telling is actually incredibly simple and kind of beautiful. See all those different colored dots and shapes? Each one is a different high-speed crash on a different material, steel, Kevlar, whatever. And here's the amazing part. When you analyze the momentum, they all fall into the same predictable zone. It doesn't matter what the material is. It doesn't matter what you shoot at it. There is a single, universal upper limit to the impact. It's a fundamental law of collision. I mean, you don't have to take my word for it. The researchers themselves said it best. They found that it's the momentum exchange that's in charge. That's the fundamental governor of the crash, no matter the material, the size, or the shape. I mean, this is a massive breakthrough for designing everything from better body armor to tougher spacecraft. So finding a universal law that works for paper cars all the way up to micrometeoroids is incredible. But it pushes us to ask an even deeper question. Just how fundamental is this whole conservation of momentum thing? Is it an absolute unbreakable rule of the universe? Well, that question has been at the center of a huge debate in physics for a solid 100 years. Let's rewind the clock.
Way back in 1924, some of the absolute giants of physics, like Niels Bohr, put forward a wild idea. They suggested that down at the quantum level, momentum wasn't perfectly conserved in every single interaction. It was more of a statistical average. But then, almost immediately, other experiments came along that seemed to prove them totally wrong, showing that, no, momentum was conserved perfectly, strictly, every single time. And for almost a century, we've had these two conflicting ideas just sitting there. Is it statistical or is it strict?
So, what's the deal? Is the universe strict with its laws, or does it just play by the averages? Well, the answer, it turns out, comes from one of the most famously strange and powerful concepts in all of physics.
The way out of this debate isn't about picking a winner. It's about realizing that both sides were just seeing a different piece of the same puzzle. The thing that connects them, the key to the whole mystery, is quantum entanglement, that spooky idea that particles can be linked together so that they're no longer independent, no matter how far apart they get.
All right, so how on earth does entanglement solve this? Let's walk through it. When particles interact, they become this single combined entangled system. Now, because they're linked, the total momentum of that entire system is fixed. It's conserved. So, if you measure the momentum of one of those particles, you instantly know the momentum of the other. It has to add up. This means conservation is always strict for the whole system. So why did Bohr and the others think it was statistical? Well, because when we look at just one particle, we're completely ignoring its invisible connection, its entanglement to everything else in its environment. It only looks random because we're not seeing the full picture.
So there you have it, from saving an egg with some paper to protecting a satellite, to the very fabric of quantum reality, the law of momentum is universal. And it teaches us something pretty powerful, right? Sometimes the deepest truths only pop out when you stop looking at the individual pieces and start seeing how the whole system is connected. It really makes you wonder, doesn't it? What else are we missing?